Good morning, friends. It gives me immense pleasure to be here again for my favorite course, Flight Mechanics. This course is in 4th semester, Aeronautical student of Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have covered basic concept of atmosphere, lift theory, drag polar, thrust required, thrust available, power available, different velocities, atmosphere, different layers of atmosphere. These all things I have already covered. Today I am going to take some very important topic, that is minimum drag speed estimation, that we have to find out. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical, Hyderabad, India. I am from Department of Aeronautical Engineering, IARE, Hyderabad. Today's overview, my topics are minimum drag speed, regions for minimum drag speed, formulation for minimum drag speed, speed stability, and one numerical we are going to handle in this lecture. If I talk about Man Ki Baat, as you know, as of now we are in the phase, different mission phases. If I make a typical phase diagram, this is the takeoff, this is the climb, this is the cruise, this is the descent, this is the loiter, this is the landing. As of now, we are discussing about mostly in the cruise flight, and we have already derived the equations of motion for the cruise flight, and in this we have find that lift is equal to weight, thrust is equal to drag. If I make the aircraft, this is an aircraft, here is the center of gravity, this is the weight should counter the lift, there will be always drag, this will be countered by the thrust. Thrust is produced by the engine, lift is produced by the wing. So for the cruise flight, this is the equations of motion. For the cruise flight, we have seen that thrust required, thrust available, power required, power available. We have also seen the maximum velocity, also absolute ceiling, service ceiling. Absolute ceiling means when the PA is equal to PR or TA is equal to TR, there will not be no excess power. No excess power is available. Aircraft will not be able to climb. Only it can perform the cruise only. So this is the something just I want to discuss about Man Ki Baat. Now I will talk about the minimum drag speed of the aircraft, something I have touched before also. And here we have the plot of drag versus the velocity. Drag is in the y-axis and it is 400, 600, 800, 1000, 1200, 1400. And this you can see here that here this drag is from here, it is decreasing up to here. Here we have the minimum drag. This is the minimum drag, and the velocity where the drag is minimum, that is called the minimum drag velocity. So this is the minimum drag velocity. In this here it is a 30 meter per second, the velocity of this plot. But here as you go more than this speed, your drag is increasing, and it will reach to some point maximum where your TA is equal to TR. So after this your aircraft cannot go up. So another important speed is where the aircraft generate minimum drag force. In level flight we know that thrust is equal to drag. So for minimum thrust, minimum drag, or T minimum is equal to drag minimum. Thrust minimum is equal to drag minimum. Drag is a function of air speed. So we know that drag is equal to half rho v square s CD, where CD is a drag coefficient. This shows that the velocity increases, drag increases. This you can see here, but not true for all speed. So if you see here, from here to here it is okay. It is directly proportional to v square. But from here to here, it is inversely proportional to v square. So that is the condition which we have to look after. Reasons for minimum drag velocity, we will see here. When a pilot is going to increase the speed, the thrust must be increased. So if you want to increase the speed V, T should also be increased. If the altitude is held constant, if your aircraft is flying in the same altitude, the aircraft angle of attack must be reduced. So if the velocity is increasing, lift will also increase. So we have to reduce the angle of attack. The reduction in the angle of attack means the reduction of the CL, coefficient of lift, and consequently a reduction in the CDI. So this CDI will be reduced. Recall that the drag force has two parts, that is induced drag and the zero lift drag. So we have the CD naught plus CDI. So this CDI, as angle of attack is reduced, the reduction alpha has to be done, and this alpha will make this CL will be reduced. So a reduction in the CDI or drag induced drag will be reduced, and recall that the drag force has two parts, that is induced drag and the zero lift drag. As the speed is increased, the CDI is decreased. Increase in velocity leads to a more induced drag. So CDI is decreased. Increase in the velocity leads to the more induced drag, DI, while reduction in the induced drag coefficient result in a reduction in the DI. So if you increase the velocity, more induced drag will be produced, while reduction in the induced drag coefficient results in a reduction in the drag, induced drag. The overall result is usually a reduction in the induced drag, and increase in the air speed increases the zero lift drag D naught, while decreasing the induced drag Di. The drag force has a minimum value when the velocity is varied. This speed is called the minimum drag speed or V minimum drag. So the drag force has a minimum value when the velocity is varied. This speed is called the minimum drag speed. So this we have to take care of. So when the objective of a flight is to minimize the fuel consumption, the pilot must select and fly with this speed. Example is mission surveillance and mission to maximize the endurance. This velocity is unique for any specific aircraft and is a function of the flight altitude. So we can see here that drag is equal to half rho v square SCD. Drag is equal to half rho v square SCD. But we know that CD is equal to CD naught plus KCL square, where CD naught is a zero lift drag, KCL square is a induced drag. So we also know that CL is equal to 2W by S rho V square. So 2mg by rho V square. From equation 2 and 3, in equation 1, if you are putting the value of CL, so D is equal to half rho V square CD naught plus 2K, here 2K, KCL square, mg square by rho V square S. If we differentiate this with respect to V and setting it equal to the 0, we obtain that del W by dV is equal to here 2V, 2 is cancelled, so here rho Vs CD, here minus, here we will get 4K mg square, rho V cube S is equal to 0. So here we can write that V to the power 4 is equal to 4K mg square by rho S square CD. V square is equal to 4K mg square by rho S square by CD. So here we can write that, and finally we can write that V minimum drag is equal to, we can further under root it, 2 under root K mg divided by rho S under root CD naught. So here 2 mg under root K, it is gone here, this, so here you will get that 2 mg by rho S under root CD naught by K, and we know that 2 mg by rho S under root, here K by CD naught to the power 1 by 4. Comparing this to the equation number 3, we get that V minimum drag is equal to under root 2 mg by rho S CL minimum drag. CL minimum drag. So the lift coefficient at minimum drag, that is CL minimum drag, is equal to under root CD naught by K. So if we divide by CL by CD minimum drag, so CL is equal to under root CD naught by K divided by CD naught plus K into CL square, so CD naught by K. So here we can get under root CD naught by K divided by, this is the CD naught and this is also CD naught, so 2 CD naught. So CL by CD minimum drag is equal to 1 by 2 under root K CD naught. So this is the condition for minimum drag. Okay, so comparing the equation 9 and 2 yield the following, that CD minimum is equal to 2 CD naught. So the CD minimum is equal to 2 CD naught. Drag coefficient of an aircraft when flying with a velocity that corresponds to the minimum drag is equal to the twice the value of CD naught. So for the minimum drag, the velocity should be, the drag CD minimum drag will be 2 times of CD naught. So it is 2 times of zero lift drag. Now I will discuss about speed stability, and this is very important. Speed stability implies that an aircraft has speed stability only at a speed beyond the minimum drag speed and does not own speed stability when the aircraft is lower than the minimum drag speed. This fact reveals a danger zone in a level flight. So if you can see here that if your aircraft is here, this is your thrust available, this is the thrust required. if your aircraft is here, this is the point 1, this is the 1 prime, and this is the 1 double prime. So what is happening here? If your aircraft is here at 1 prime, then you don't have that much thrust available. So your aircraft will tends to come to its equilibrium position. It will reach here. Another case, if your aircraft is flying in this speed here, and here thrust available is more than the thrust required, so this aircraft will tend to move to again in this point 1. So here point 1 is stable case in speed. So if your aircraft is flying from here to here, your speed stability is existing. But if your aircraft is flying here, assume this is the point 2, and if you extend here, then what will happen? If you see here, in this case, your aircraft is flying at V2 speed, but due to the available of the thrust, your aircraft will not go in this direction. It will not go. It will go in this direction. So at point 2, it is trying to go beyond its equilibrium. Equilibrium is here. So it is trying to go away from the equilibrium. So point 1 is unstable in speed. So here it is unstable, and here if you are, this is the 1 and this is the 2. These are the stable and unstable points. So our aim is to fly our aircraft somewhere here. It is stable, but if you are flying here, this is the unstable zone, and this is the stable zone. So pilot will always try to fly from here to here. It will be always advisable. It is not advisable. This is unstable zone to fly. So I am going to explain about explanation of speed stability. So jet aircraft, when the speed is lower than the minimum drag, the speed is lower than the minimum drag, say V1 is less than V minimum drag. Now assume that a wind gust reduces the aircraft speed to V2, which is lower than the original speed of V1. So this V2 is less than V1. Then what will happen? Since the speed is decreased, the drag is decreased, equation 3.1. Consequently, since the drag is decreased, the speed is increased further. The story is continued until the speed reaches the stall speed, and even the decrease in speed is continued. We know that an aircraft is not able to maintain level flight if the speed is lower than the stall speed. Thus, this incident causes the aircraft to stall first and then have a fatal accident. So if like this situation, the aircraft will meet with accident. So just I am again explaining the same thing here. This is the PR, this is the PA, power versus velocity. This is the point 1, this is the point 2. So if this 1 is here and flying at a less than this speed, but power available is more, so it will try to increase the velocity and it will reach here. If it is here, power is less, and it will try to decrease the speed and it will try to come. But if you are here, this is your stall speed, we stall, and you are flying here, then what will happen? As you are here, it will not try to go here, but it will increase the velocity. This increase in the velocity will not have the sustained, and it will try to go to the stall zone. So it is dangerous. Now I will discuss one small problem. Problem number 2.4. A small jet aircraft has the following features. M is equal to 2500 kg, S is equal to 20 meter square, CD naught is equal to 0.03, K is equal to 0.06, V stall is equal to 75 knots. A. At what speed this aircraft must cruise such that the engine produces the minimum thrust at 10,000 feet? Repeat part A when the aircraft is flying at sea level. So at 10,000 feet, what is the status? And at density at 10,000 feet is given 0.412 kg per meter cube. So these are the things we have to solve the problem now. So we know that CL for minimum drag is equal to under root CD naught by K. CD naught is given 0.03, K is given 0.06. So we will get the CL for minimum drag is 0.707. From atmospheric table, which is given in appendix B, the air density at the altitude of 10,000 feet is 0.412 kg per meter cube. So minimum drag is equal to 2 mg divided by rho SCL minimum drag. 2 into mass is 2500, 9.81. Rho is 0.412 into 20 into 0.707, which we have got from here. We have put this value. So V minimum, we got minimum drag. We got the 91.7 meter per second or 178.3 knot. So this is the minimum drag at which aircraft is flying. That is the case 1. But if we fly at a sea level, this rho will be same. So rho is a 1.225 for this. So the V minimum drag is equal to 2 mg by rho SCL minimum drag. So 2 into 2500 into 9.81 divided by 1.225 into 20 into 0.707. So V minimum drag is equal to 53 meter per second or 103 knot. So if you are flying at a lower altitude, your minimum drag speed will be less, and this is the more. So that we have to understand that if we fly the aircraft at low altitude, minimum drag velocity will be low. That is why pilots are flying at high altitude, so that their minimum drag velocity will be high, so they can fly with a high speed and they can save the fuel for the different purposes. So in next lecture I am going to take about these topics: state and level flight, engine types, performance criteria are discussed, fundamental equations, velocity and angle of attack relationship, and then one numerical we will be discussing in our next lecture also. I am referring these books: Anderson J.D. Jr., Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. Esselby, M.E., Aircraft Performance, Theory and Practices, AIA Education Series, AIA 2. Any questions you are welcome to ask. I also request do subscribe and like this channel. Give the comments in the comment box, so that if anywhere I have done some mistake or anything you want to improvement, please do write. I will try to implement your suggestion. Thank you very much for listening this lecture. Very soon I am going to take another lecture as given in my previous slide. Those topics I am going to cover. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.